Hello everyone, my name is Kacper Trębacz, and today I'd like to present you my project for density estimation for distributed learning. My mentor is Jack Good, and my advisor is Professor Arthur Dubrowski. Why do we want to use distributed learning? Let's imagine a scenario when I have three hospitals, each of them having sensitive patient data. They'd like to learn a common machine learning model together. However, due to the local regulations, they cannot send data. What the distributed learning proposed instead is to send models instead of data, and then learn jointly a common model utilizing those models. What's the difference between centralized federated learning and distributed learning? In centralized federated learning, there's a central server coordinating the work between nodes, and in the distributed learning, there's no such server. All the nodes are independent and communicate over a predefined communication graph. Currently, the most commonly used approach in distributed learning, as well as federated learning, is parameter space regularization. And ongoing work at the Auton Lab proposes to use a different approach, which is to compare the models in the function space instead of the parameter space. So, in the parameter space regularization, we enforce the agreement on a model by adding an additional penalty for the model for having its parameters too far from its neighbors. And whilst in the function space regularization, we don't compare model parameters, but their predictions on the entire domain, and we want them to be close to each other. So how does the learning process look like? Let's imagine we have two clients. Here we'll describe a scenario of extreme data imbalance, meaning each client having only data belonging to one class. So at the first step, the clients learn their models and then send them to each other. And in the next training iterations, they use each other models as well as their own data to learn the next models. And after a few such iterations, we have at the model that have very similar predictions on the entire data domain. What we noticed during training is that for some datasets, the performance gap between centralized models and the distributed models is significant. We suppose that it might be because in high-dimensional datasets, data tends to occupy small subsets of the space, leaving most of it blank, and we still enforce agreement in these spots. What we propose to solve this issue is to use weighted function space regularization. So instead of enforcing agreement on the whole data domain uniformly, we introduced a weighting function, which is estimator of the density of the data to weight the agreement by this density. We propose two approaches. First of them is to weight the function space by leaf density. It works by keeping track of how many points were used during training of the decision tree, and how many of them were in each leaf, and then weighting the space by this value. So, for example, in the left leaf here, there was 80% of the data, and in the right one was 20% of the data. So now the model would give higher value to the left lift than to the right lift because there was more data there during training. The other approach we propose is to train a Gaussian mixture model to estimate density of the data, and then use it as a weighting for the function space regularization. Thanks to this, in the model when there is data, the agreement will be higher than in other places. So it looks as follows. So for the weight by leaf density method, the method is simply lambda, which is our regularization hyperparameter, divided by the weight of the leaf by the remaining number of training examples in the leaf, divided by the number of training examples in the root leaf or in the whole dataset. For the Gaussian mixture density estimate, we use diagonal Gaussian mixtures in order to be able to factorize the density into marginal distributions, and but during the inference we don't use Gaussian density of the Gaussian distribution, but we approximate it with logistic distribution density because it has a closed form cumulative density function. Thanks to this, we can get the weight of the leaf by calculating the cumulative density function at the upper and lower bound of the leaf and dividing the result at the lower bound from the result at the upper bound, obtaining the probability of that leaf. We also introduced two baselines, which are sampling baselines. We enforce agreement by having a so-called agreement dataset. Agreement dataset is some set of points that we include in the training data for which labels are predictions of neighboring models. We introduced two baselines. First of them is holdout baseline, which uses just part of the training dataset as the agreement dataset, and the other is GMM sampling baseline, which first trains a Gaussian mixture model on the data and then samples a set of points from that data and uses it as the agreement dataset. We conducted results on 3 artificial datasets using the May classification function from scikit-learn, which are datasets made by sampling from Gaussian distributions. I will also test on 5 popular machine learning datasets, and for the synthetic dataset, we can see a huge improvement over our uniform function space regularization model by even 16%, which shows that the good density estimate can improve the results. And on the real-world datasets, either the Gaussian mixture density estimate or the leaf density estimate improve in 4 out of 5 cases. We only get slightly lower results for the vehicle dataset. So, when it comes to conclusion, we have shown that the density estimate that is close enough to the data can greatly improve and really improve performance. And when it comes to future works, future directions that we want to dive in, we want to test distributions that are different than Gaussian and logistic. We want to develop models that would allow us to select good hyperparameters for the density estimate itself, some rule of thumbs to use. And also we'd like to test it on models other than simply decision trees. Thank you very much. I'd like to thank Jack Goods and Professor Artur Dubrawski for their mentorship and support, and the organizer of the RISS program, mainly Professor John Dolan, Rachel Birkin, and Morgan Grimm. Thank you.